get cracking. Well, we'll skip why do we care about minimizing DFAs for a second. And go to actually number 2, which is a nice warm-up. Minimize that DFA. Unless it's, so easy that it pains you. Then you can move on. You stop doing your homework. Yeah, this is going to be a tough class to tape because there's a lot of dead air and people are working.
You should do a dance routine.
Yeah, I guess we could have like musical interludes while you guys are working.
Get Rusty in his banjo.
Yeah. All right, I guess we can start. First, before we tackle number 2, which is like the simplest, one of the simplest ones you could do, that will explain things a bit. Give me 2 reasons why we want to minimize DFAs.
Because size really does matter.
Size matters. Okay. I guess it's a meta reason. Yeah. So they don't like this in Texas, you're saying, like small DFAs. Like the big.
Let's just not go there.
Yeah. What?
You're being recorded now.
What's that?
So you're being recorded now.
Oh, yeah. I just offended like a huge part of the country. You're saying. All right. It's true. No baloney tree moments. All right. No. Well, there's a theoretical. Let me narrow it down. There's a theoretical reason, and then there's like a practical reason too.
Well, it helps us compare them. Yeah, we're able to compare them.
Right. So the theoretical reason is it's a normal form. The minimal form is it's the normal form for DFAs. So it lets you know if 2 ones are the same. When you're proving something about them, you can reduce it to the minimal one. It's a very nice thing to know that you can always do. So that's the theoretical reason for it. It's the canonical normal form. Lets you solve things in a very methodical way. Just minimize it and then do something. So it lets you program a computer to manipulate DFAs. What's the practical reason? Well,
We're actually trying to build one of these things sometimes.
right? So there is a practical use for these things, right? These are control logics for simple machines, like switches and little doors or something. Who knows what?
Garage door.
Yeah, garage. They're control logics for all sorts of things. Therac 25, irradiation machines, all that. So you minimize the complexity, you save some money, you get a raise. Your company does well. So it's good to, smaller is better. All right, so that's why it's good. So what's the answer for this? For number 2? A and C get joined. So Andrew, you were asking, how do you do this? Right, so what's the principle? Can someone remind me? So we're trying to figure out which one of these are different. Which two, so there's 3 things here. Which ones are definitely different? We can't collapse these 2 because this is not accept, this is accept. So they're definitely different. These are definitely different. These are the only possible ones that are the same. And how do we know if they're the same or not?
We check to see what they're dependent upon. Their phase are different.
So what does that mean? we're testing to see if they act the same. If they behave the same in every possible way, they are the same. Right? They're indistinguishable. And how do they behave? Give it a 0, this goes to B. Give this a 0, it goes to B. Give this a 1, it goes to C. Give this a 1, it goes to C. They look the same. Well, they talk the same, they act the same, they are the same. They're exactly the same. All right. So that's the essence of the whole algorithm. All right. Okay, so what about the next one? Did you guys finish that? Who? I hear one, yeah? I think everyone else needs some more time. Give it a bit more time. By the way, do you recognize what this DFA is for? Yeah, this thing is the last number is a 0. All right.
Oh, wait a minute.
What?
Well,
It's not all. It's
I
not,
noticed there's a 1 that goes from the B to the C, but not a 1 that goes from the B to the A. Is that a
For
problem?
2?
For 2.
Oh, here's a good question. Maybe these aren't the same because this guy, B goes to C, but B doesn't go to A. So maybe they're not the same. Is that a valid argument or not? B's pointing to C, but it's not pointing to A. Right, we're only interested in the behavior once you're in that state. Right, if you collapse these together, then B is pointing to both of them, but that's fine. That's fine. It's only like future performance, I guess. That's really important. What is this thing, what are you going to do given you're in that state? What is pointing to you has no effect on how that state will behave in the future. Where you came from, doesn't tell you anything about how you behave when you get there. You behave exactly the same whether you came from here or from there, or from wherever, given a certain input stream. But that's a good question. All right. Make sure you all got the next one. By the way, what is the next one? You recognize that? This one's going to take a while, but it's good. Good practice. Yeah, it's this. Oh, it's great. Yeah. Question. Oh, more? There's more. Yeah. Whoops. I got some challenging problems at the end there for you, if you're interested, if you're willing. Willing taker. It looks. No, no, that's not it. But it looks close. What's your question? There's a way to do it that way. The thing is, certain things will become equal, but then those equalities will cascade backwards. So things that don't appear equal will become equal. Right?
So here I have, for example, B, D, and F, and C, and G. Is that correct?
No, you have to be careful. Actually, why don't we? One thing is things that are accept and not accept can never be the same, even if they have the same transitions. So B and D, one's accept, one's reject. They have the same transitions coming out of them, but they can't. They're distinguished another way.
All right. So except for that. So okay, I can see that.
Actually, that's a good question. Take an aside here. Here's a proof. Well, it comes up here, but it also comes up here. Let me write down the transitions for A on 0 and 1. On 0, it goes to B, and on 1, it goes to C, right? Correct? Yep. What about B? On 0, where does it go? It goes to B. And on 1, it goes to C, right? So I claim that A and B are also equivalent. So I can collapse this all into one thing. Because they behave exactly the same way. You feed it a 0, it behaves that way. You feed it a 1, it behaves that way. So that can't be right. Where's the error in my reasoning?
So there's a difference. One is an accept state. On an empty, then one of them stays in the accept and the other one doesn't.
We got 1, 2, 3 answers, and everyone else? Does everyone appreciate what the question is? So they act the same. Why are they different? Yeah, this is final. You can't just look at the transitions. This is a final state. That's not a final state. Thank you, everyone.
If they were both non-final, then you could say.
Yeah, if they're both non-final or if they're both final, you could collapse them together. But it's easy to forget that. The base case is whether it's final or not final. So you have to use that. And then, yeah, once you figure out things that are equivalent, you can propagate that backwards.
I guess it's the same as the beginning state.
No, the beginning state doesn't matter. You can collapse the beginning state with other things. Remember, an arrow pointing in doesn't affect you in any way.
If you do the transition table, we always have to indicate whether it's an accept state or a start
Right.
state too. And that's how you differentiate between two rows which otherwise look the same.
Right.
If you
Right.
forget that, then you run into trouble.
Right. All right. You want to work through this?
Is Shy's method the way we should do this?
We'll do both methods, the Shy and the Heather method. All right. So what would the Shy method be? So we start with B, C, D, E, F, G, and then A, B, C, D, E, F. All right, it's going to be tough for me to draw straight lines. But I'll try. My darndest. Yeah. All right, so we got to put on all the differences first. So D is certainly different to everything but, or different from. Excuse me. That was a terrible lapse in grammar there. D is different from everything but E, right? So we can just cross out, put X's everywhere there because, and same for E, it differs with everything but D. So we can put X's there. Now, I don't know, we can kind of do this in an ad hoc way. I mean, you could be systematic about it, but you can just look at it. I mean, certain things. Am I missing a transition? Well, I mean, you can eyeball it. Certainly, so the things that are, we differentiate between things that are accepts and not accepts, right? Now we can differentiate between things that go to an accept. You know, so F goes to accepts. So it can't be the same as G, because G on one input goes to reject. So now we're like looking at the sort of extended family instead of just, you know, we're looking at all the relations. So on 0, F goes to an accept state, and G doesn't. So certainly, for example, F and G must differ. I guess we can just systematically, well, you can just do it by the graph instead of looking at the table. I mean, so clearly, what other things must F be different from? It can't, this goes to 2 accepts, so it can't be either A or C, right? It might possibly be B. So F can't be A, and F can't be C. What about B? What do we say? B can't be A, because B goes to 2 accepts, and A doesn't. A goes to 2 rejects. So it can't be A or C, right? So we can get rid of BA and, where's BC? Right there. All right, are we missing anything else? B and G can't be the same, right? Right, for the same reason, because G goes to 2 accepts, non-accepts, and B doesn't. So we have all those things. All right, what's left? There's A and C. Well, and again, another sort of rule of thumb is it's good to start kind of at the end, if there is an end, and then work backwards. If I started trying to figure out whether things were the same here, I'd have to go all the way down to figure out the story. But if I start here, and you know, there's a better chance that I'll be able to figure things out if I work backwards. Yeah? Okay. So what about, are there any you suspect look the same? B and F you suspect? Anything else? G and C? Yeah, all right. So both of those actually should be pretty easy. Right? Are they the same? What does B do on a 0? It goes here. It goes to D. What does F do on a 0? It goes to D. So they're the same that way. What about 1s? They agree with 1. So we can collapse these two. They're really the same thing. They act the same. They're in every possible way. So B and F are the same. Check. All right, so these are the same. Now what was the other suspect? C and G? What about those? On a 1, where does C go? To G. On a 1, where does G go? To G. And what about 0? Same. They go to the same place. right? So those are the same too. They act the same. The transition, they're both rejects. You have to check that also. So C and G are the same. And what about what's left? A and G. Oh, there's A and G and A and C. So I guess, so now we can say, what about, where does A go on a 0? It goes to this blob, the BF blob. Where does it go on a 1? Well, actually, stop. A goes to the BF blob on a 0. And where does C go? It goes to the same thing, to these equivalent things. So A and C are behave the same for zeros, and they behave the same for ones too, right? They both point to this collapsed CG node.
This is why you want to start at the bottom.
Yeah, it's good to start at the bottom. If you can. So this is kind of like incorporating. This is an easy problem. I mean, because we can visualize it. Anything you get to do personally instead of programming your computer should be relatively easy. And if you can exploit, exploit things like this. You always try to propagate backwards from these nodes, from the accept nodes. Now, why couldn't a computer do that? Why couldn't a computer propagate backwards?
It doesn't know the graph yet.
Like, we're just eyeballing the graph, and we can tell what's pointing to this. But usually on a structure like this, it can't figure out what's pointing to it unless it actually does a search. Right? We can just do that visually because we have this great visual processing hardware. And we can see, these things are pointing to that. Right? So unless that's specifically programmed in the data structure, that's going to take the computer a long time. The thing that's trivial for us to see, what's pointing to it. That's going to take it a lot of time. So that's why the Shy method is actually very good for a computer. It's dynamic programming n squared. It's very nice. If you actually did it propagating backwards this way without exploiting some like parent data structure, then it would be an n cubed algorithm, it turns out. But that's not important. Anyway, so A and C are the same. Yeah. So it looks like this. What's that? I haven't done D and E? I haven't done D. No, we did figure out that D and E were different.
Did you talk about it? I don't think we talked about it.
Oh, I guess we didn't. Well, D goes to accept states. D only D visits accept states, on any input. E goes to reject states. So they can't be the same. They act differently. All right, so what do we have? So we have something like this. So on 0, it goes there. I'm confused. Oh, these are all the same. That's why. On 1, it goes to itself. Got the 0, got the 1. Got the 1. Got the 0. What are we missing? The 1 goes here, and the 0 goes here. Did anyone figure out what this was? By any chance? No? I'll tell you, it's not important. It's actually a lot like this one. This is the last thing is a 0. This is the second to last thing is a 0. See, because you go, all right, if we get a 0, no matter what we get, we accept on the next stage. If we get a 1, no matter what we get, we reject on the next stage. But then if you get let's say you get a 1 and a 0, then since the last character read was 0, it's just like being here. Yeah. So this tree is just enumerating all the possibilities for this remembers these states remember the previous 2 characters read. So 0 0 0 1 1 0 1 1. So but that's too much information. All you really need is you don't need all that information. So it can collapse. It's kind of interesting. I wonder if it collapses. If you do it gets really pretty. You keep on doing third to last thing is 0. I wonder if it probably collapses like that. I haven't thought about it. But it probably collapses diagonally. I don't know. But anyway, so there you go. There you go. That was that. You can skip the next one. That's just, you pretty much know how to do it. Oh, we have to do the Heather way. Well, you know, I haven't ever seen the Heather way before, so this is kind of scary for me, but I'll try it. So A, B, C, F, G. D and E are different, right? Because they're rejects. So I 0, 1. So D stays in the club.
Yep. D stays in the club.
E goes to F, G. So who stays in the club? A stays in the club.
Yep. B goes to DE.
DE.
C stays.
Do you know what I mean by stays in the club?
You don't go to the other group.
Yeah, it stays in this big group. C stays in the club. F doesn't, right?
F goes to
DE. And G goes to, stays in the club.
G stays.
One little thing I don't know if I've made clear before, is when you say it like B goes to D and E, what you should really think of it as is B goes to the club, D is in.
Right.
Yeah.
So B goes to DE and DE.
And D, as long as DE are in the same club, you're okay.
Yes, thank you. All right, so what happens now? So we get
ACG.
ACG. Hey, that's pretty good, huh?
No, but you have to
We
have to relook at them.
Huh?
Look at them
We have to
You
again.
have to relook at them because they might have changed.
But I know they don't. I'm sorry, I'm jumping ahead. No, they don't. They go to a different club. You're right. All right, and then we get.
And then draw a line.
All right, it's not as easy as I thought. B,
B and F.
BF,
BF.
and then
And then you have to separate D and
D and E is separate.
are separate. Yikes! So A. So help me out, someone.
A goes to the BF club on 0.
A goes to the BF club on 0, and it stays in the ACG club on 1.
And same with C and same with G.
It goes to the ACG club. Where does B go on 0? It goes to D,
It goes to the D club
the D club,
the D club.
and the E club.
and the E club. And same with F, right?
D club. E club.
And those are already singular, so we don't even have to evaluate them.
Hmm.
Yeah, we don't have
You're right.
to
Okay. I was just curious where they went.
D stays.
D stays with themselves.
D. This is DE. These will have to be. They have to be different, right?
Yeah, that's what.
It's a good way to check if you made a mistake too. So E goes to F,
And G.
FG. You don't really have to do this, but if they were the same, you would have screwed up. You know, it's a good error check. So those are the groups. So that's I mean, it's the same. It's a very similar argument. You know.
Yeah.
Yeah, I guess. Then drawing that, I guess. Yeah. Good algorithm.
Maybe this one might be easier.
Good algorithm. All right. So that's it for that. All right. What else do I want to talk about? All right. I guess we'll give. I want you to give a grammar for this right here. Problem 5 says give it for the previous problem, but I inserted a problem since then. So it really refers to this. I'm very sorry about that. I just noticed. So, well, hopefully it doesn't affect a lot of people. Yeah, so turn this into a regular grammar. Does anyone need a word of explanation? What that means? I know you do. No? I was going to come around. How many people could do that? Turn this into a regular grammar. What's a regular grammar? Well, so it's something of the form like A, start goes to 1, A goes to 0, or 0, A, or epsilon, something like that. You guys all comfortable with those? No? No? All right. All right, I'll give you some examples first. Yeah, it's the same as a linear, left linear grammar is a regular grammar. Okay. All right, so let me give you an example then. I'll go reverse. I'll give you a grammar, and I want...
Linear grammars also grammars? Are also regular?
Um,
Because the reverse of the string is also regular?
yeah, I guess maybe I have to think about... I'm not sure what the definition of linear grammar is. That's why, what it refers to exactly here. Right, you're right. Right. Regular grammars are also right. Linear grammars are also regular. But let me do this problem. So what if I have something like S goes to 1A, A goes to epsilon? What language does this represent? What? Can you give me a regular expression for what this is?
Just one.
It's just one. Because if you follow the rules, you start here, drop a 1 and an A in there. A is only epsilon. It's just the language 1. But now, what if I had... S goes to 1A, A goes to 1A or epsilon.
It's all ones. All
Well,
string with
So you have to have at least one 1, and then you could have more of them. You could go 1, A, and then expand this into 1A. So you get 1, 1A, et cetera, et cetera. So this is 1, 1 star. Right? And it gets more complicated. Why don't I turn this machine here into 1? It's actually very, very simple. Right, so start is there. So if I get a 1, I go to C, right? So I say S goes to 1C. If I get a 0, I go to B. So I just do that. So S can either go to 1C or 0B. All right, and then what? Basically, this is S. Yeah, so you just put in something for each transition. So yeah, what does B go to? It can go to 0B. So 0 and then another, and do it one more time. Or 1C. Or to epsilon, I can just say stop. It's allowed to stop because of that. And C goes to 1C or 0B, or that's it. All right, so why don't you do that for this one and practice. Or do something else if you know it already.
The grammar for the minimized or the original?
The minimized one, just to give you guys a break.
Are you drawing it right now on the board?
Yeah. Because I erased it accidentally. Let's see, I have it here. 0, 1, 0, 1. All right, and I guess I'll say S, B, C, or B, D, E. I'll call them B, D, and E.
That's supposed to be on 0.
you got 2 D's.
Uh-oh. That's a D. Just so we can have consistent notation. All right, I want to see some answers. Yeah?
On the minimal machine, this is accurate. You don't need that arrow. It could be a self loop instead. But that's no different. Because you're just saying the next to last character is a 0? You could either loop on itself or it could go off to the start state.
No. No, it couldn't. There's a reason why I couldn't.
No, you're doing
Oh, it has to go back and allow another single zero to come in.
Right, it has to get, because if you get 2 1s,
Uh-huh.
I see what you're saying. You're
It's
saying
just-
you could just go this way.
No, I was claiming that you could just loop on.
Oh no, the
one
difference
here.
is because this is an accept. This is an accept.
D&D. Okay.
Yeah.
Mhm.
So these are accepts. So if you loop back, you get an accept.
Right.
If you went there, it's not accept.
I should have written
Yeah.
my circles. Yeah.
Yeah. Those accepts will trick you every time.
So would this be acceptable if we didn't split it up by ors, but instead just put it out like?
Yeah, you could write it out like that too. Yeah.
Okay. So I'd split it up. Well, not like. Well, like before, but just like not A, B, D, but instead just A, B, C, and D.
Yeah.
Yeah.
Yeah, that's fine.
Okay.
Looks good. I don't know. Check with your neighbor.
I did. She didn't know either.
Why not?
I think I just have different,
Different letters.
I'm looking at the same thing.
Oh, I
He drew a different one on the.
yeah, I did.
Oh, he
The reference.
I haven't done that
See.
before yet.
Oh, sorry. The reference has changed. Wow. There's no 1 here actually. That's the 1 is. Oh, that should. That's the 1 is actually going back to S. I should have. I erased that, but I didn't erase well enough. Do we have answers? Yeah? All right, so what's the answer? No, it's 42. All right. Quick.
This goes to 0B.
Or 1? S. Okay. Huh?
B
Quick.
goes to 0D, 1E.
All right, so this is mindless and trivial, right?
D goes to 0D, or 1E, or empty.
Trivial.
E goes to 0B, 1S, or empty.
All right. So final states can go to empty set. Yeah. All right. So they're not so bad, huh? All right, so the question is how to turn regular expressions to grammars. Let's see, well, why don't we work through that? I think there's some ad hoc rules. You could always turn it into a machine. But you don't have to turn it into a machine.
These guys are simple enough that you don't.
Yeah. So what about A? What could you do? S goes to 0, B. B goes to 1C. And then what does C go to? 0C or epsilon. There you go. So this is how you can make, you can add tons of new letters wherever you like if you have some complex structure. So you start with S, then you get 0B, and then you get, say, we'll derive, say, 0, 1, 0, 0. You go S, 0B, 0, 1C, 0, 1, 0C, 0, 1, 0, 0, C, 0, 1, 0, 0, epsilon. That's how I got, say, for example,
So if you
that.
draw the machine, you don't actually draw the arrows that don't connect. Like say, like I did like 0B or 1S. If you're drawing both arrows out. That, like you move back to the
Huh.
start.
So the question is,
Sorry. If you were actually to draw the machine out, like when converting it, instead of like actually writing
Yeah.
it out first, because I draw it and it's
Uh-huh.
better visually. Seems like you have to have a 0 and 1 going out of each state.
yeah,
And so when I did that, I had
more stuff. Yeah.
more expression.
Yep. Yeah, if you draw the machine, you'll get more expressions.
And that's
More complicated thing. Is it okay? Are we going to take marks off of you?
no, I mean, is it the standard? I mean, is that
Well, it's better. I mean, if you can describe something in a compact way, that's always better. Because it's easier to understand. I mean, this characterizes 0, 1, 0 star a lot better than, a whole bunch of symbols. But usually it's obvious when you can make reductions too. Yeah?
Can S go to 0, 1 B?
It could. That wouldn't be like a linear grammar. Yeah.
Only one
Yeah.
symbol.
Yeah. So it turns out if we modify these rules a little bit, then we'll get things like if we can have symbols on both sides of this, then we'll get things that aren't regular expressions. We'll break the pumping lemma. Like if we had S goes to 0B1 or something, then we can get 0 to the n, 1 to the n. But we'll talk about that in a bit. So these things are more powerful than. So if we just do rules like this, where the characters are on the left, then that's just like regular expression. All right. Really quickly then, what about this one? A, B, or B, C star? What do you think? So S goes to,
A, and then some symbol.
so it goes to A, F. And what does F go to?
Empty or
ABF, empty or ABF plus ECF.
Well, we can't just do two. We want to do it using just using regular notation. So epsilon or
AG or VH. We need 2 more states.
yeah, I guess.
2 more.
Yeah, is that what I did? I'm getting confused now. I hate it when I get confused. Yeah. Okay. So A. So it'll go to A. Oh, I'm so confused. Help me, someone.
Simple. Big symbol. G.
All right, AG. I guess that's right. AG or
BH.
BH. I get it now. And now G goes to G goes to BF.
That's it.
Is that right? And H goes to CF. Is that correct? I'm so confused.
Those letters.
That's good. That works.
You would put the F in the second line also instead, right?
So you're saying A, G, F? What do you mean?
Well, that won't work because
Or F? That's pretty circular, right? That's like an infinite loop if you do that.
But that's okay, right?
No, because then how do you... So let's say I start. I go, okay, S, A, F, A, F, A, F, A, F. That'd be really bad if I kept on substituting F in there. My computer would have a fit. Yeah, so you can't do that. So that's why you kind of have to make up a new symbol and do the recursion that way. Just like what we did here. Yeah, there. These are confusing, huh? All right. Next thing is this is a good one. Yeah.
If you loop again, let's say the first like A, then AB, then do BC again, is that allowed, or do you have to do AB, AB, AB? Repeat?
A.
When you have like the parentheses star, do you have to do?
You can do
Either one.
You can do A,
Yeah.
B, either
Yeah.
way. Repeat it, okay.
You can do either one. Yeah.
So I guess probably what I meant was FF then.
FF?
No, because you can't have two non-terminal.
Not in this sort of setup. For left linear grammar, we can't do that. Right? The only things we can do are split up into two things. Like one is a terminal. Or no? Yeah. That's what Shai said? All right, I'll trust him. I'm sorry, I didn't. I have to look that up, actually. But I believe that's the case. In any case, moving on. So look at number 7. Here's an argument, your favorite sort of argument, that arbitrary number of zeros followed by an arbitrary number of ones followed by an arbitrary number of twos. That language is not a regular language. So you could use the pumping lemma, like you all know and love, right? Or I have a better idea. I say, well, I already know that arbitrary number of zeros followed by arbitrary number of ones is not regular. And this thing contains that. It contains something that's not regular, so it's not regular also. Is that valid or not? Valid reasoning. It already contains something really weird, and we've proven that's not regular. That's enough, right?
We never said anything about 0 to the L1 being not regular.
Because there was 0 to there.
Oh, L equals M. I'm sorry. Yeah, those are all equal. Greater than or equal to 0 and equal to each other. All right, sorry about that. Of course. Because otherwise it's 0 star, 1 star, 2 star. Yeah. So what I mean is, yeah, L equals M equals N in 7. So I should say 0 to the N, 1 to the N, 2 to the N, and 0 to the L. I don't know what I was thinking, but there you go. So anyways, we already showed this was not regular, right? And this is, oh God, this is what I mean. Yeah.
A different number of twos.
All right, so this one is having issues, this problem. Maybe my whole point was that just because you show one thing is regular and then you have a bigger thing, or you show one thing is not regular and you have something bigger that contains it, doesn't necessarily mean that's also not regular. You can't use that line of reasoning. You know, you have to sort of, that's false reasoning. Because like the universe, you know, like the language that has everything contains non-regular sets. Right? 0, 1 star contains tons of non-regular sets, but it is regular. So you can't just say, argue that way. All right. So I've got to fix that. That's on the to-do list. All right. I guess the last thing is maybe some decision algorithms. We'll go. So why don't you, who can tell me? I'll start you off. Give me a decision algorithm. So some way of figuring out whether a language L whether a language L contains the string 10000101. So I have some language given to me via regular expression.
What do you mean by decision algorithm?
So a decision algorithm is something you could program into a computer. Let's say you have a representation for the finite state machine or the regular expression. Can you give me an algorithm that decides? So if I give you finite state machines, can you give me an algorithm that decides whether that machine accepts 10000101?
Just run it through the machine.
Run it through the machine, right? So what's the point? Why am I bringing this up? So the point is you can actually treat machine as data. So what I'm feeding you is not, you're switching the thing around. I have the 10000101 with me, and people are, that's like the program now. And people are feeding me machines. And I'm deciding if that machine is good or not, if I accept it or not. So so the machines are the language now. The set of machines that accept 100001 is a language itself. The really freaky thing here is everything is a language. I guess that's what I wanted to talk about. So everything is a language, right? Everything is strings of data, right? Programs, the data itself, the input, they're all strings of data. So you can think of them, as numbers too. It's kind of a really, it's a trippy thing to think about. Like I was thinking about it, like, yeah. I was like, whoa, man. No, for example, all right, so this is going to be a philosophical digression for a second. Do you believe that numbers exist? So like, do you have to actually observe the number for it to exist? Like, you have 1, 2, 3, 4, they all exist. And we know there's infinite number of numbers because we can always keep on adding 1. But do all those numbers exist without our having ever written them down? Or not?
So if a number falls in a forest?
Yeah, exactly. If a number falls in the forest,
Isn't that what dot 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 is for?
dot, dot, dot. But I mean, most people believe that all the numbers exist, right? Even though you haven't bothered to check that it's there. You haven't personally checked that 5,993,000 whatever exists. It's probably there, right? You believe that. But now the thing is, the really weird thing is that since everything is a number, this does a lot of weird things to creativity. For example, like if you look at MP3s, I think every MP3 can be encoded in a binary string, which is in the range of 2 to the 10 million to like maybe, let's give it, every reasonable like pop song, I don't know, or song that we listen to. It's in this range. That's like a very rough range. So every MP3 is a string that lives in this range. Okay, it can be encoded. And all these numbers exist. We just said that, right? So what does that mean? That means that not only every song that's ever been written exists there, but all the future songs are also in there too. Which is very strange.
But isn't that,
No, but the numbers exist.
but wait a minute.
Isn't that strange?
MP3s are compressed to a standard of our ability to hear. Now, our ability to hear could improve in the future.
All right, so I could give you a bigger range, but like,
So what you're arguing is
or I could give you literature or something. You could do. There's a range for all books too, which is within 100 pages.
So why don't you copyright them all?
Yeah, I was going to copyright all these numbers and make a fortune. No, but what's my point? It's not philosophical digressions. The point is that everything is a number, and it starts getting very weird. Not only are the numbers numbers, but the music is a number, literature, the programs are numbers, and you can treat the programs as input too. So in number 9, the program is plug. This is a meta program. It's not a finite state machine. It's a Turing machine, which we'll talk about later. But it's a program that takes other programs as input and it evaluates them on 1,000,101. So everything is like completely backwards. What you think is data is not. It's the program. And what you think is the program is data. And that's where you're going to get all sorts of weird things. And like Gödel's incompleteness theorem, if you ever heard that. Heard of that. So let's see. I guess it's time to stop. I'll let you guys think about the other ones. There are more elaborate decision algorithms, but you don't have to do any of them for your homework, so that's fine. And I finally fixed number 12 is that problem that I kind of messed up last time. So that one is interesting because it's an example of, it's totally miscellaneous, but it's an example of where you can get rid of epsilons in an NFA without doing any like horrible subset conversions to DFAs. So figure out if you can get rid of the epsilons there. That's a little problem. And the last thing is applications of regular expressions. I guess it's just a promise right now. Rusty and I are working on this. There are really good applications to regular expressions. A lot of cool programs you could use in Unix to make your life easier. And we'll try and give you an introduction to that. So there's a little practical thing to regular expressions. And hopefully you could, hopefully we'll build a calculator. Machine that calculates. So that's our goal.
More existential exercises.
You want more existential exercises? Oh, this thing is chock full of them, and this subject is just crazy. But I guess that's it for now.